Can you all please settle down? How was the session yesterday? Good? Interesting? Okay, so today we are going to have a talk about the edge of artificial intelligence, self-driving medical image analysis by Fanindra Yalavarthi. Fanindra Yalavarthi received BSc and MSc degrees in physics from Sri Satya Sai University, Puttaparthi, India in 1999 and 2001 respectively. He also obtained a MSc degree in engineering from Indian Institute of Science, Bangalore, India in 2004. He received a PhD working as a US Department of Defense breast cancer predoctoral fellow in biomedical commutation from Dartmouth College, Hanover, USA in 2007. He worked as a postdoctoral research associate in the Department of Radiation Oncology, School of Medicine, Washington University in St. Louis, USA from 2007 to 2008. Currently, he is working as a professor of medical imaging in the Department of Computational and Data Sciences, Indian Institute of Science, Bangalore, India. Please enjoy the session. Over to you, sir.
Okay, thank you very much for that kind introduction. Am I audible and my slides are visible?
Yes, sir, yes.
Okay, thank you very much. Before I go further, I have a bunch of conflict of interest because I work with a large amount of private companies. Here they are listed here. Even though I'm presenting this work, at least the work which has been carried out in my lab has been carried out by the students and the postdocs, and as well as it is done in collaboration with several collaborators. So I would like to acknowledge all of them here. The brief outline I would like to do is that, I would like to introduce the medical imaging to start off. I assume that, a lot of you may not be coming from the medical imaging background. And then I will talk about a little bit about autonomous medical image analysis. And then I will talk about AI, artificial intelligence in the clinical use. And then dabble into a little bit into our own lab work, which is related to COVID-19 chest CT anomaly detection. And then I will also end with some of the new topics or the challenges for any of you who are interested in getting into this area. So let me start off with the medical imaging as an industry. Currently, medical imaging is considered as a $30 billion industry, with roughly about US occupies about 50% of the share. And what is expected is that, Southeast or South Asia, which includes India as well, currently its share is about 20%. It is expected that it will reach to 35% by 2025. So that's why it is known as the emerging market, and there is a lot of push for making viable products for the emerging markets. Having said all this, there are only 4 major manufacturers in the imaging industry. GE, Siemens, Philips, and Canon are the 4 major players. There are players which are on and off, but they are not major in some sense in terms of imaging equipment and how the radiology works. And again, we talk about this on the sustained growth. And there is only one other industry which has recorded the sustained growth of at least 6% annually. That is another industry is digital media. So other than that, medical imaging is the only industry which has had the sustained growth of 6% in the past 3 decades. And we have a concept called going from concept to clinic, or we say that any major medical imaging equipment development, including insurance claims, will take about 3 decades. So that means that in your lifespan, if at all you assume that your work life is for 3 decades, you are going to really develop only one equipment if at all you are successful. So again, if you are looking at in terms of intellectual property, and I have done a search around December 2021, I have not done in the recent times. Roughly, it shows up as 3.5 million patents which are directly related to medical imaging, and then they are still growing. And of course, we say that the bar is too high to go from bench to bedside. Of course, everything has to be, medicine is always evidence-based. So unless you establish the evidence, it will not go to the bedside. In the recent past, at least in the last 2 decades, the major emphasis has been on the non-invasive procedures. The interventional or invasive procedures have been more or less discouraged due to various issues, but emphasis is on non-invasive. Today, I don't think there is any major procedure in the clinic that gets done without imaging being involved. So it has become indispensable in the clinic. So again, let me just say that formally define the medical imaging and then move on from there. So let me just try to get a pointer here. So when we define medical imaging, actually it is a visualization of the lesions or disease or under disease. So that means that what we would like to do is that using imaging, we would like to visualize those lesions or the diseases. And obviously there is a radiological interpretation because of the visualization, which gets done by either by the clinicians or the radiologists. And then when they interpret, what they do is that they rule out or rule in a diagnosis. So if somebody is suspected of cancer, they will say, yeah, the cancer is positive or negative. So of course, by the time it comes to the visualization, there are a bunch of things we do. First is to acquire the images using scanners. And this is a raw data, or you can call it as non-imaging data. And then what happens is that after this acquisition, we convert that into images. You can call this as reconstruction or computing, or we also do enhancement of the images. So in some sense, people like me, those who work on this analysis part, all work in the space of converting something like a raw data into useful images such that the radiologist or the clinicians can interpret better. So that is essentially where we come into the picture. Of course, if you are talking about artificial intelligence as well, the artificial intelligence also comes into the play in this aspect of converting the raw data into something more useful for the clinicians to interpret. So again, in terms of utility, so there are many imaging modalities that exist in the clinic because each one of them give a different information, or we call it as, you can think about when will they be relevant depending on what information you are seeking. So for example, like computer tomography will be very useful to find out the morphology. The morphology means that primarily you are looking at the structure. But if you are looking at the physiology, how well they are physiologically functioning, then we got to look at either MR or to a certain extent to the ultrasound if it is a soft tissue. But if you want to look at metabolism or molecular level information, so then you got to look at either nuclear medicine or optical imaging. Again, just to put in the perspective of the cancer. So when you have cancer in less than 10 to the power 6 cells, we call it as neoplasia. So the neoplasia, if you want to detect, that is, you can call it a stage 1 of the cancer. Ideally, you should be looking at either metabolism or molecular level information. So by the time we do the diagnosis using either CT or to MR, we are already in the physiology sector or morphology sector where it is beyond stage 2, or at least stage 2 and beyond. So in some sense, if you want to detect the cancer, you got to look at these, finding them at the metabolism level or the molecular level if you want to do it at the initial stages. So again, so there is, if at all I have to divide the needs of the people, in some sense, there is something called a science needs and there is something called what clinic wants in terms of what medical imaging should do. So, we have listed these clinical needs. What everybody wants in the clinic is that they want a faster imaging sequences. They want cheaper. They want less radiation. They want to screen and they want it to work globally. And of course, the major emphasis is on early detection. We were just talking about stage 1 of the cancer. Of course, there are a few other things which you could do. And then in terms of scientific one, can you look at high resolution images? Can you look at single molecules? These all become the basic sciences needs. The one which I have put in the box, which is talking about clinical imaging in terms of faster, cheaper, less radiation screening, and working at a global level and early detection. This is where everybody thinks AI will make a difference. Our artificial intelligence will really play a big role in terms of making this a reality or meeting these needs in some sense. So even though I have said that there is an interpretation that gets done by the radiologist, but typically this we call it as image-based tasks. So if at all you think about workflow, we acquire the data, which is raw data. We do some amount of processing, either reconstruction or enhancement, and we form these images. And based on these images, there are certain tasks which needs to be done. That is what we are calling it as interpretation. And that interpretation, based on that interpretation, you make these reports. The reports based on these images which are available. And those reports go into what is called as diagnostics. So that means that imaging alone will not be part of the diagnosis. So they will look at other parameters, maybe some of the diagnostic tests which are already there, some of the genomic data, some of the clinical data. They look at clinical correlation and make the appropriate diagnosis. So what are these image-based tasks? So essentially, we divide this into three types. One is the detection. So that means that simply to put it in the deep learning world, it is a binary task. We just want to know whether there is a abnormality or not. So it's like saying a positive or not. And obviously, this is a little more easier if you have to characterize. So in terms of characterization, what we want to do is that if at all there is an abnormality, you want to know, how big is that tumor is, or how much width it is having, or what are the features it is representing. So that this becomes more of quantitation. For this, we require to do segmentation and evaluate the abnormalities and do some amount of staging based on the markers which we have found in this. And then later comes the monitoring. So if at all you are following up the patient, somebody is going through the cancer treatment, you would like to know whether the tumor size is shrinking or it is regrowing back in some cells. So this is called as change analysis, or you can also call it as longitudinal analysis. So you would like to look at different time points, how the features have changed over the time. So now, as you would have imagined, that detection is the little more easier task, and then characterization is a little more harder task because it requires reading up all the images more carefully and then characterizing each of the image. And then the monitoring is even more tougher because not only you have to characterize the current scan, but you also have to correlate with either previous scans as well. So, and again, just to put into the context, because I have shown the lung image here. So typically in the HRCT, which is high resolution CT, the number of slices available for somebody to look at it, or number of images available for somebody to look at it, is about close to about 200 images. So that means that even to do a detection, so what they need to do is that they need to, the radiologist needs to read through 200 of those images. Even for detection, even assume that it's going to take about 3 to 4 seconds for them. So even that will turn out to be something like looking at least 10 minutes of each one of the patient data, just to say whether there is an abnormality or not, or even to do something like binary kind of classification, whether positive or not. So now imagine that you want to do characterization or monitoring, it is going to take even more time. So now again, why this is where we think that the AI will play a major role. And then more importantly, what happens is that even though we are talking about data here, most of the healthcare data, if you look at it by volume, 90% of the data which is aggregated or which are there in the hospitals is actually medical imaging data. So these are they consume most of the space because essentially they're all set of images. Most of them are 3D volumes or 4D volumes. I just now spoke about the chest CT, which is occupying 200 images, and so that consumes a lot of space. So even though there are other types of data which are available, but imaging data becomes essential part of analyzing. So if at all you want to do anything data-driven innovation or data-driven analysis, so it has to start with images. So then only we can move into other data and then look at other parts of the things. So now this is where I'm going to change the gears and talk about a little bit about autonomous medical image analysis. So to do that, I'd just like to introduce the autonomous vehicles to start off with, and then go on to this image analysis part. So now currently there are these automation levels of autonomous cars. So now, for example, like, I don't know whether you have observed or not, the level 0 is there are no autonomous features. So the level 1 has at least one task at a time. So for example, like the ABS, which is anti-lock braking system, is actually an autonomous feature. So if at all you are having ABS, most of the cars on the road currently have ABS. So that is a level 1 autonomous car. So that means that you are already driving autonomous car. The level 2 is that it can do two automated function. Assume that along with the anti-lock braking system, you have automatic deployment of the airbags. So that is another automated function. So at least you have a level 2 autonomous vehicles. Today, most of the vehicles, I will say 90% of the vehicles on the road, at least the four wheelers, the cars, they are all level 2 autonomous vehicles, even in India. So the level 3 is that they can handle the dynamic driving task, but still might need some intervention. So for example, like the XUV 700, which has been just released. So that is of level 3 autonomous vehicle. So the level 4 is that they are officially driverless in certain environments. So currently, most of the Tesla cars which you are seeing, they are officially driverless in certain environments, not all the time. That is level 4. So level 5 is that they operate entirely on their own, right, without any driver presence. So that means that they are truly autonomous. So the level 5 is what everybody would like to achieve. What we are at is at level 4. And if at all you want to look at the development, what has happened is that in about 2010, we were at level 2. And in about 10 years, we have come to level 4, or at least the Tesla and other cars are at level 4. So if you ask, when will we become level 5, right? So where 75% of the vehicles will become truly autonomous. So what is expected is that at least it will take about another 2 to 3 decades to get to that kind of autonomous, right? So completely being autonomous, which is level 5, we can only get to be in our about 3 decades. Even though in 1 decade, we were able to move from level 2 to level 4, but that last part, which is moving from level 4 to level 5, where we are making completely autonomous, is going to be the crux of things, and that is going to consume more time. So this is where we have to do the analogy to the image analysis. So for example, like if you ask me, there is a data which exists, and then you want a screen, right? So I told you, right, the detection is more like a screening. So where you want to know whether there is a lesion or not. So this is like a binary class where you want to say positive or negative. So that part is going to be probably like, making some autonomous things like, probably like level 1 is what you want to get into. So that, again, if you ask me level autonomous, what will be the cost somebody will pay for it is extremely low. It's about $1 to $10 is what typically people pay. But you want to get into the diagnosis part where you want to characterize what you have detected as an abnormality or a lesion. So that is where, where little more money exists, at least, 2 to 3 times more money. You can call this as level 3 thing, where you are talking about somebody is having a grade 4 malignant tumor, or somebody is having a grade 3 benign tumors. So things like that. So you want to, that is little more on the diagnosis. But of course, the ultimate pinnacle is that, you are doing screening, you are doing diagnosis, but can you also suggest the treatment? So that is what is the clinician makes the decision. The clinician makes the decision that this patient is having a grade 4 malignant tumor, and they need to go through either radiation therapy, or they need to go through surgery, or they need to go through immunotherapy. So those are the decisions they take. So that is what Mr. Smith should receive the specific treatment. So now you are telling them to take what treatment, or you are recommending certain treatment. So that is where you make most of the money, or major money exists in this. Of course, the value chain wise treatment is what ultimately everybody want to achieve. But right now we are somewhere between, I will say, screening and diagnosis. We are not even between diagnosis and treatment. So we are getting between the screening and diagnosis in some sense, what AI is able to do, at least in the medical image analysis. And that is what reflects in almost current clinical deployments. If you look at either Canon or Philips or anything. So whatever I have told you, for example, like, I'm just quoting what Siemens has released in the recent one. It has released AI-based software assistant for chest CT to identify and measure lesions. So that means that it is doing screening and then doing a measurement of the lesions. It is not even grading them, but it is measuring those lesions, right? So now the Philips one has like a platform embedding AI empowered models for screening and prioritizing the cases. So here we are still at screening. So in very simple sense, almost all the players are either in the screening regime or little bit pushed towards diagnosis. So nobody is able to get into the treatment as of now. So we are hoping that will happen in the next 5 years to come. So that is what comes out to this. So right now, if you ask me, we are at the screening and diagnosis. That is where I have put it. This is where we are right now. But what we want to achieve ultimately is that, can we get into the treatment planning? And then we would like to look at augmented thing getting done by the AI. So in very simple sense, if you ask me where we are in terms of equivalent to autonomous vehicles, we are able to do one or two tasks which are there in automated fashion. So I will say that currently we are at level 2 equivalent for the autonomous vehicles in terms of medical image analysis. Of course, it is going to take another decade for us to move to the level 4. I don't think we will achieve level 5 anytime, because completely being autonomous is not something which the clinic would like to do, because still healthcare has to have some human touch to it. So let me just again go back, and then I have given analogy between autonomous vehicles and the medical image analysis and current development. I will just get into the AI clinical use to a certain extent. Of course, I might be repeating what other people have repeated, but just to refresh your memory. So the current regime of AI is all about deep learning. So where we don't want to do any feature engineering, we want to learn the feature on its own. So what it has is a neural network which will take the data and then it will give an output by going through a high level feature extraction from it. And what currently the traditional machine learning, or what we call it as feature engineering, used to do is you take the image and then you would like to pick a feature, right? So this could be based on intensity, which is based on histogram. This could be based on shape. This could be texture, based on what expert feels right. So the experts could be people like me. We have been trained on the imaging physics. And then what we say is that, the texture should look different between what is a malignant tumor versus a benign tumor. So we pick one of the features and we select that feature. And based on that feature, we can do a simple classification. This classification can be achieved by something like SVM, or even assume that, like, if you want to go with unsupervised, something like clusterings like k-means or fuzzy means, you can do that. So this is what, but it requires a feature to be engineered or to be chosen. And then we got to extract that features, and based on that feature, we can do the classification for whether it is benign, malignant, or whatever classification we are behind. So very simply, for example, let's assume that we are looking at the breast cancer, and then we would like to know whether this lesion is benign or malignant. So the traditional deep convolution neural network, what it will do is that you just give the image, it will give you the prediction. As long as you have enough training data, you are able to do it. But in the traditional machine learning world, where you have to extract the feature and then go through a classifier to make the predictions. Now, the problem with either of them, either machine learning, which is part of the AI, or deep learning, which is the part of very thing, is that they don't really universally work for all images across the patients. And the generalizability is always a problem in either case, right? So even the feature I have extracted may not be the universal feature for all the patients to work. And any of these AI tasks are task dependent. So that means that they're able to do only one. For example, if I have extracted one of the feature, and here my task is to predict between benign and malignant, can I use the same feature for looking at what grade tumor I'm looking at? So that may not really work, right? So that means that the feature I have extracted, or I have engineered, or I have learned is only for this kind of prediction, which is benign versus malignant. It may not be useful for other things, even though you can argue saying that I can do transfer learning and make it go to other tasks, but that also requires us to retrain most of the time. And especially the feature extraction part, where we are talking about feature engineering part, requires understanding of imaging physics and clinical knowledge. So in some sense, it is not learning on its own. It still requires some imaging physics and clinical need. Even on the deep learning side, because the data in the medicine is always very, very limited. So having any prior knowledge will always help us in terms of getting the better models. So now again, I would like to put this as a challenges in the medical imaging. Of course, I don't have answers for this. And again, I would like to say that each one of these questions is a big research area by itself. So I won't go into giving you some of the solutions, but everybody should realize that each one of these questions is a area by itself, and people work to answer their lifetime to answer one of these questions. So essentially what we have is a data, and we might be developing AI model. And ultimately we are coming back to the result part. So in terms of data collection, we can ask the question, how many images do we need? So for example, in the case of where we wanted to predict whether it is benign tumor versus malignant tumor, how many really images do we need to train the model? So let's assume that, I have said that, I require 300 benign, 300 malignant, and then, 300 normal. Now, what happens if we don't have enough data? So, and as you would have realized already that, getting the normal data might be easier, but anything, if you are one of those persons who is working on rare diseases, so the data itself is sparse, right? So the number of people who are having the disease itself is very less. So among that, you have to collect that data. So that might be a challenge. So what happens if you don't have enough data? Okay, you have the enough data. Let's assume that, whatever data you needed, you got it, but you don't have the annotations or you don't have the ground truth. Because remember, the ground truth has to be assessed by an expert, and the expert time is money. So now if you don't have enough resources or if you don't have enough experts also, how will you do if you don't have enough annotations? Now, in terms of the model itself, right? So this is all about on the top part, which is about the data part. Now let's talk to the model. So now we can ask the question, right? So now I spoke about something like traditional machine learning, and I also spoke about the deep learning part. Do we really require deep learning models? That's a question we want to answer, right? Or assume that we want deep learning models, but is there any off-the-shelf models which we could borrow and use it for the task at hand? Now, again, I spoke about prior information. We can also say that it is a context also we want to include. Because typically the radiologist, when they are interpreting the images, they will get the patient history, they will look at the patient history and then always assess it in the context. So how can we incorporate that context or prior into the models? So is there anything which I could do in terms of including that? Or is there any more trainer friendly or user friendly models? For example, like, if you are in a resource constraint setting, so how will the AI algorithms get into this, right? So this is the question we always have in terms of those. And then in terms of result interpretations, then we can say that how can we visually interpret the result? So AI has given some result. So how will you do this? And then can we obtain a human friendly interpretation? So if I know how radiologist is interpreting, so can I say that, my AI model is also trying to look at the same region or looking at the same interpretation? Again, so as I said, each one of these questions is a big area by itself. Again, to be brutally honest, each one of the people like me, we only work on one of these questions. For example, my lab works on mostly on more trainer friendly or user friendly models. So this is what we focus on. Of course, you can work on any of these, and any of them are very, very exciting. For example, on the explainable AI, where we are talking about results interpretation. So there is a lot of work that is going on in some sense. And then even in terms of data collections, in terms of augmenting the data, so there is a lot of work that goes on as well. So now let me just answer some of those which are related to the models, because our work involves a little bit on the models. This is to make sure that some of the students can really appreciate this. So the reason why you want to use the deep models is that you want to make sure that they are better than the humans. So remember, the humans always have this tendency of getting tired. So maybe in the morning I'm really sharp and I'm able to do more things done, or maybe I'm able to do things precisely. But as time progresses, right, by evening I'm really tired. So I may not be the same person as I am in the morning, right? So there is a variability in terms of performance, and more importantly, there is a variability among the experts as well. So now, for example, what I consider as benign might not be considered as a benign, right? So it all depends on the experience, expertise, and training as well. So, for example, somebody who's a senior resident might give a different interpretation compared to somebody who has been an expert in the field for a long time. So that means that essentially you want to get to the deep models because you want to remove that variability part. And wherever the traditional machine learning algorithms have given good results, and you want to improve the performance of the traditional machine learning algorithms, then you would like to use the deep learning models. So typically it has been shown that if traditional machine algorithm is able to give X performance, at least with deep learning, what you could expect is that it will be X plus 5% more, at least 5% more accuracy you can expect. But of course, this assumes that you have more data available for training. So even the data set, the training data set should be even more larger for the deep learning models to train. Of course, on the off-the-shelf models, this is essentially for the students. So if at all you are looking at the image segmentation, I will say that, look at the UNet. And this is a very standard model or baseline model everybody should implement if at all you are doing the segmentation. You will see that even in our own work. It works well with small annotated images. So when I say small, something like about 300 images is good enough for it to work reasonably well. So there is a VNet if you are looking at three-dimensional image segmentation, which is an expansion of the UNet, but it has some residual connections and it learns some of the residual functions. These are a little more harder to train, but you can do the volumetric segmentation using the VNet. And if at all you are looking at a lot of variable data, which has, for example, like in the skin cancer or even in the diabetic retinopathy, you have a lot of variability in terms of the illumination patterns, in terms of the camera characteristics, camera specifications, image specifications. So you might have a lot of variability in the color coding, color schema. So in those cases, something like inception networks or even combined with ResNet type ones will work very well because they will be more suitable for removing that variability and making the diagnosis or analysis easier. So now this is what leads us to our lab work, where we work on what we call it as mobile friendly lightweight CNNs. So now remember that any of these networks like UNet or even including the VNet type ones, they all require high-end computational resources while training and as well as the deployment. So now the problem is that when I'm deploying, I might want to deploy it in the field, right? So now imagine like I have a screening cabs which I'm doing out of a mobile van. So in those mobile vans, now I can't put a high-end GPU like which is worth like $15,000 and then expect it to work there, right? That defeats the whole purpose. The screening has to be as cheaper as possible. So now can we generate some of those CNNs which are lightweight, which can be deployable in like mobile phone or mobile platforms, such that you don't require any specialized hardware to deploy the AI models or to get the inferences done. So of course, there are certain edge devices which NVIDIA type ones already provide. For example, Jetson is one such example, which comes with a GPU which occupies very less space and it's also cheaper. So you could also deploy it in that. Of course, as I said, there is a fast inference, easy deployment on mobile ones and embedded platforms. How to develop this, I will talk about it in a while. But essentially, what we would like to do is that these are more mobile friendly, or trainer friendly, and user friendly algorithms, or deep learning models, which we would like to do. Because our main aim is to go into the point of care and essentially address this starting problem of either diagnosis or the screening part at a resource constraint setting. So now how to develop this? So there are essentially four ways of doing it, or combinations of the four also you can try. So the first one is that you can develop the lightweight deep learning networks using a low rank approximation. So where you essentially look at this and then think about like regularizing the solution and reduce the parameter space. You can also do something called as network quantization. So which essentially means that you can make everything which is which is having a double and reduce it into single format, such that you can do some quantization, such that the amount of parameter space which you are looking at in terms of memory will reduce. And you could also do knowledge distillation. This is called as teacher student model as well. You can train a heavy model as a teacher, and then as a student you make a lightweight CNN and do the knowledge distillation from the teacher to the student. There is also something called as network pruning, where you look at the connections and then you kind of remove some of those connections, such that you can make it the parameter space much lesser as well. And of course, there are certain tools which are already available which will do automatic network quantization or network pruning in some sense. So I'll talk about the network quantization in a while. But of course, you can also start thinking about designing it from scratch, these lightweight deep learning networks. So in terms of this, so this we call it as deep learning at the edge. When you want to get into the point of care diagnosis, you got to deploy on the edge devices, not really on the heavy models. So this is called as deployment of the edge. So you can think about there are three steps to it. One is design. So you can really design the model thinking that you are going to deploy it on edge. The edge device could be a mobile phone, it could be a Raspberry Pi, it could be a simple laptop which you are looking at. And then you develop it, and then you do deployment in terms of those. So in very simple sense, you have the data. Always we do pre-processing of the data. We make it ready for the training. And then you can design the model. You can do the training, validation, and testing on this. But when we want to deploy it, we want to generate what is called as lighter versions of these models. And there are already tools available, right? So for most of the deep learning folks who are already working on it, TensorFlow and PyTorch are the two Keras. TensorFlow, Keras, or the PyTorch are the two major ones which everybody will use. So there are certain versions where when you give the regular model, it will do the quantization for you and generate a light model. So these light models you can you can deploy it on a device like an Android or Raspberry Pi or NVIDIA Jetson for that matter, so that it becomes easy for it to deploy it on the edge part. So now again, what are the examples of the lightweight CNNs? Remember I mentioned about the inception, right? So where we were talking about removing a lot of the variabilities. Those are part of the lightweight CNNs. So there are also mobile networks which are already available, which are done by the Google in some sense. So those are also kind of considered as lightweight CNNs. So there are these efficient nets which are scalable models which start from lightweight to heavy. So depending on what you are looking at. So this will move into our lab's work. Where we worked on effective management of COVID-19 using chest CT. So with that, I know, and after that, I have one more topic called new topics, and with that, I will stop. So let me just give you how does the COVID-19 progress over the time. So this is a simple case of chest CT where we are looking at a patient with the COVID-19. So now what happens is that I would like you to concentrate on these red boxes. What happens in this case is that these red boxes, you can see that within about 5 days, the red box had more of this infection, or we call it as anomalies. So this has grown in the anomalies. Somebody who recovered from this will not have those anomalies after this is after a month, and then they will completely have a remission in about 6 weeks time. Right. So that is what is roughly shown here. So now one of the problem which has been given to us by the clinicians is that especially during the wave 2 in India, one of the difficulty which all the clinicians had was who was a candidate for to be admitted in the ICU and who should be admitted in the regular ward and who should be given a home treatment. So this is what has to be assessed. So what we wanted to do was that we wanted to give a scoring based on those anomalies, essentially segmenting those anomalies and finding out of the total lung volume, how much they are occupying. So now this is called as CORAD score right now in the normal one, but this is pre-CORAD score, which I was talking about. So if you have 0% abnormality or 0% infection, we call it as normal. If it is less than 25%, we call it as mild infection. Less than 50%, we call it as moderate. Less than 75%, but above 50%, we call it as severe. And anything above 75% is extreme. So as you would have imagined, the people who are having infection greater than 75% is what you would like to admit them in the ICU. Maybe between and 74 is what you would like to admit them in the regular wards. And the rest of them probably you can manage at the home management. So this is what we wanted to do. But again, we have the constraint that we wanted to make sure that it works in as a point of care model such that we can deploy it in resource constraint setting. So essentially what we wanted to do was that take the HRCT images, extract the lung, and then run through our algorithm, which will give this percentage of the abnormality, which will essentially the segmented part. So for this, we kept this in mind that we want to deploy it in a point of care setting or in an edge device. So we started designing this network from scratch. So we have used something called as anamorphic depth block. So where we have done something like a bottleneck, which will do a depth squeezing and then 3x3 convolution at the same time, at the same depth, and then again it will do a stretching. So this will act as a good regularizer. for us to get the feature space better in terms of embeddings are slightly better regularized compared to the regular unit type. And the last function, which is a critical part of any deep learning one, we have used a weighted cross entropy. Essentially, we had three labels. One we call it as background, which is non-lung. Another one is normal lung. The third one is infected lung, or COVID-19 anomaly. So we have used this three class problem. So, because there is a slight imbalance in the how much is there in the background, how many pixels are there in the background, and how many pixels are there in the normal, and how many pixels are there in the anomaly, we had to do some weighted cross entropy. And then we have done this as a part of the training. So again, what data we have used, of course, right now these are available as open source, but essentially we have used close to about 70 patients data, and there were a bunch of slices which were available to train our network. And as I said, UNet becomes the base model for everybody to compare because that is what is considered as a thing. And what we have done is the AnomNet which is proposed. So for example, like UNet has close to about 31 million parameters. So whereas what we were talking about having about 4 million parameters, and the model size itself is about 17 MB, which can easily fit into the mobile phones. And even I'm talking about training time being only about half an hour, and inference time is about 1/3 of a second. And if you are comparing that with UNet, so you will observe that you will require about an hour to train, which is about double of what the training time which you require. And the inference is also takes more time because there is more competition to be done. And even though we have done in terms of the lightweight, we have not compromised on the accuracy part. The accuracy has turned out to be very good in this, and even the dice scores have been turned out to be state of the art. Of course, the only other ones which has competed is Unit plus plus or the Unit, which we expected. But our model was much lighter and easily deployable in the mobile phones. And again, these are set of results which it is showing what is the ground truth and what we have predicted in terms of the anomalies. We have deployed it on Raspberry Pi, which is again, a simple edge device which you can think about, and it was able to run in it. We have even done it on NVIDIA Jetson. We also had an Android application which you can download and then deploy it as well. And those of you are interested in this Android applications, so this is an AnomNet which is available at this link in the GitHub page. You can download and then do the processing. So obviously you could have seen that what happens is that you load an image, and then what it does is that it will essentially tell you what is abnormal region, what is a normal region in terms of percentage. So that is how it shows up. And so those of you are interested in a little bit more on the looking at the architecture, and then how did we go about either training or validating this, you can look at this paper. So this was published in TNLS last year. And we have gone ahead, and then we said that may not be worthwhile because getting a CT scan done is something which may not be possible everywhere in India. So can we do this using a lung ultrasound? So whereas ultrasound is a very common equipment which is available across India, so the penetration of the ultrasound is much more. So can we look at it and then do a point of care detection of COVID-19 using this lung ultrasound images? Again, this was a lightweight network which we have designed based on more like MobileNet V2 type. And then this was also published. It was a core page article in terms of this, what we call it as mini COVIDNet. So again, before I close, at least I would like to talk about a little bit about the new topics, and then I'll come back. So we started off with the question about whether what happens when you don't have enough data. So how many we read, and what happens if you don't have enough data? So this comes back to what we call it as synthetic medical images. So can I synthesize the medical images, in some sense from either from other modalities, or assume like we are really looking at virtual reality type ones. Can we synthesize those images? Of course, we are looking at generative adversarial networks, which are GANs, for generating those, which will look like real ones. And then we are also talking about, you may remember, the image-based task needs to be converted into the reports. So can AI automatically write those reports, or at least give the draft reports? So that we call it as image to text. And then even in the pre-processing stage where we are converting the raw data into images, which we call it as image reconstruction, can AI have some more models there? Because currently, if you look at like something like HRCT reconstruction on a lung, once we have the raw data acquired, it takes anywhere between 40 minutes to 5 hours to reconstruct that into images. So can AI do so that it becomes more faster? And even imaging physics also. So can we talked about incorporating some of the context or prior. So can the imaging physics also be included in this AI model such that it can do a better job? And currently most of the I will say, when I say most, I'm talking about almost 99.99% of the models have only unidirectional approach. That means that you give an input, it gives an output. So there is no way for me to give any feedback as a clinician saying that, this is wrong or this needs to be improved. I want the AI model to look at this region more carefully. So drawing some of those attentions where you can talk about bidirectional interaction is currently missing. Of course, the bidirectional interaction is required because you want to have human in the loop or expert in the loop give better input such that you can incorporate the context or prior into the model very well. And more importantly, so this is something which is the holy grail of the AI or deep learning is. So currently the way we are doing things is that we have the data, which is the raw data. We do image reconstruction, we form the image, and then from the image, we extract the features. So for example, like in the COVID-19 case, which I've just described, our lab work, what it was doing is that it was segmenting out or extracting the anomalies from the image. And from that, we are telling how much infection is there. And then ultimately that infection rate or infection percentage is deciding whether somebody should go into the ICU or somebody should go into the normal ward or somebody should go for home isolation. So this was the actions which we wanted to take. So why to go about going from data to image to features and then to actions? Why not go from directly data to actions? As I already said, to reconstruct the images itself, it might take anywhere between 1 hour to 5 hours. You are losing precious time. So why not just look at the data itself, which is a sinogram data or raw data, and then get into the actions. If at all your deep learning algorithm is really capable of doing that, maybe they're not that much interpretable. The sinogram data may not be interpretable, whereas images are more interpretable, right? So in some sense, can I do this? Can I get into the data to the actions using a deep learning? So that is something which a lot of people are excited about, or what I think is becomes a reality in the next 5 years to come. Of course, as I said, right now we are only still getting into the features and we are only still at the characterization phase, which I will call it as level 2 autonomous systems, not really getting into the level 3 or level 4. Now, this is another way of looking at it. Now, if you ask the radiologist, where does the AI is playing a role right now? Right now, so this paper was published in about 2 years ago. But then I don't think it has made a big difference. What everybody thinks is that it's currently working towards enhancing the imaging quality and triaging the images and some optimizing the workflows, right? So the automated part of the image analysis, which everybody thinks that will come in the next 3 years or so, and then the clinical decision support or identifying the new indications is a little far away from there. So currently we are only at enhancing the image quality, which is at the low level, and triaging the images, which is again at the screening level, and then optimizing some of these workflows to overall productivity. Again, I will say that that is at level 2 autonomous vehicle level. So this is where I will stop. Thank you for this opportunity, and then I'll be very happy to answer any questions. Thank you.
Thank you, Professor Panindra, for the wonderful talk. And the students here are really benefited from you introducing the medical imaging space and also talking about your own work. So we'll open up for a few questions. Okay, so I'll just start off with one question. So you talked about using lightweight CNN for prediction and segmentation purposes. So how do we look at the trade-off between performance and making the model lightweight right here?
So as I said, so see again, I would like to go back to the the tasks which we are having, right? So for example, in this case of at least in the COVID-19 case, what we were talking about is is only essentially segmenting out the COVID-19 anomalies. Even though it is a segmentation problem, essentially we are looking at only 3 classes. So it is not really a multi-class problem where we are looking at thousands of classes. Like typically the computer vision looks at thousands of classes. Whereas here, our task is to look at whether among the HRCT, we got to say what is background, what is normal lung, and what is infected lung or COVID-19 anomaly. So the task at hand is quite simple, right? It's a 3-class problem. So essentially, the lightweight CNNs which we are talking about here are essentially telling that they don't compromise on the accuracy because the task itself is simple. Maybe if a task is to get into 1,000-class problem, maybe there is always a trade-off between this, but at least the model which we have shown has not really compromised anything on the accuracy part. That is essentially our analysis is that because it's a simple 3-class problem.
Professor Phanindra, another question. I saw the metric where you incorporated the time in this as a factor, as a feature in the edge devices. Why should time become the 500 milliseconds or 300 milliseconds become an entry there? Because after all, it's an edge device. And is there any difference between this 1 hour of training required with the half an hour training, those two features, why is it so important to be there in that metric?
Oh, very good. So that's a good question, right? So I didn't answer this, or I didn't include it in the thing, right? So remember, I have already mentioned that most of the deep learning models have a problem in terms of generalizability across the sites. So for example, like I'm just giving an example here that you have Apollo Hospital which is there in Hyderabad and Apollo Hospital in Bangalore. So now the model which got trained in Hyderabad may not work in the Apollo Hospital in Bangalore, because the reason is the protocol, the image sequence which has been followed, or we call it as imaging parameters that have been chosen, could be different, because every center, every site will have its own protocol. So now essentially, if at all it has to work, we got to get that model. And again, you can call it as fine tuning, you can call it as transfer learning. You got to retrain at the particular site. So this is number 1 problem. So in very simple sense, there is no model that works across the sites. So every model has to be fine tuned for a particular site, keeping in mind. So that means that there has to be some amount of training data available at this, and then we have to utilize it. So this is essentially what is required. So that's why the training times becomes an important for the deployment at a particular site, because we got to do the training there and we want it to be as fast as possible. Again, in terms of the inference time, you can also call this as a latency time. So now essentially here we are talking about a situation where we are talking about to say how much infection is there in the lung. But now you can think about like image guided surgery, where you want to make those decisions such that you want to perform the surgical things. That has to be done at a very, very less latency time. So it cannot be even in the milliseconds. I will say that the inferences has to come in the microseconds, such that you can help the clinicians or surgeons to do a better surgery. So that's why the inference times also becomes very, very critical part of it.
Okay, yeah. So are you also talking about the application side of it? So the edge-based device, do you think it's going to become more of an application in the primary healthcare setting than being at the tertiary hospital?
So even at the tertiary hospitals, right? So even at the tertiary hospitals, see, anything which has to be pushed into either into the cloud or into any of the central servers is always a lot of problem in terms of privacy, or even in terms of security. Anything which you do it on the edge, which is at the current site, has little more compliance or little more easier for anybody to look at it. right? So in very simple sense, even though we are not talking about something like pushing it to the cloud and getting the inferences, there is one problem of network connectivity. But more importantly, I will say that at least the medical data has to go through some of the privacy things, and that becomes a major issue. So anything deploying on the edge is always welcomed because it has better compliance to the security norms or privacy norms.
Okay, thank you. Any more questions? Okay, thank you, Professor Panindra, for joining us online, taking off some time from your busy schedule. Thank you so much for joining.
Thank you for inviting me. It was a pleasure.